So if you haven't appreciated the power of the chain rule from that previous segment, I hope you'll appreciate it after this, because now we're going to get the derivatives of all the functions we haven't yet figured out the derivative rules for, almost for free using the chain rule, and using what we talked about the very first week, the power of inverse functions. Let's start with ln of x. We don't know its derivative, but we do know the derivative of its inverse function, right? The derivative of the inverse function of ln of x is e to the x. So we know if I let f of x be ln of x, I'd like to find out f prime. I know that if I write e to the ln of x, I should get x. In other words, if I write e to the f of x, I will always get x, because e to the x and ln of x are inverse functions. They undo one another, and we end up with just x. Because I know this property about inverses, and because I know the chain rule, we're going to get the derivative of ln of x without doing much work at all. So now we can take the derivative of each side. And this same technique we will use 3 more times. So on this side, I've got e to the something. What's the derivative of e to the something? That's e to the same something. But then the chain rule says we have to take the derivative of the inside function. My inside function is named f of x, so that's f prime of x. But as always, if you take the derivative of one side of an equality, you've got to take the derivative of the other side as well. So the derivative of x is just 1. Now what are we trying to solve for? We're trying to solve for f prime of x here, right? So I need to divide this to the other side. So f prime of x is 1 over e to the f of x. Remember, f of x here is natural log of x. So this is our formula for the derivative of natural log of x. But what is f of x? It's ln of x. So that's e to the ln of x. But as we defined, the way that we defined ln of x is that it's the inverse of e to the x. So this is just saying 1 over x. So what we have found is that if we let f of x be ln of x, we put that into its inverse function, and then we apply the chain rule to take the derivative. We get the derivative of ln of x virtually for free. So the derivative of ln of x is what we just figured out, 1 over x. We did not have to use the limit definition. We didn't have to draw any pictures. It was just by understanding how inverse functions work and by having the chain rule. So in the chain rule, if you know the derivative of one function and you know the chain rule, you can always find the derivative of the inverse of that original function. And one thing that you might find interesting here is that when we took the derivative of a power function, what did we get? We got a power function. Derivative of an exponential function, we got an exponential function. Derivative of a trig function, we got a trig function. The derivative of a log is not a log. It's 1 over x. The derivative of a log is actually a power function. So that must mean that, and you can think about this on your own, there wasn't already a different power function whose derivative was 1 over x, or x to the negative 1. Try to imagine what the m would have had to be in the power rule to get an answer of x to the negative 1, and you'll understand why there wasn't a power function whose derivative was 1 over x. In fact, we had all the other powers already taken care of as derivatives. We knew there was something missing. We had yet to find a power function whose derivative was 1 over x. And now look, there it is. ln of x pops in to fill the hole. It is the function whose derivative is 1 over x. B to the x. We conjectured last time that its derivative was b to the x ln of b, and we promised that we would prove it this week. So let's do that here. So we know we can do something similar here. We know that if we take, we know that b to the x is the same as e to the ln of b to the x. I hope you agree with that, because if I put something into ln and then I put that answer into the e, they cancel each other out. But we have a log rule which says, what can I do with ln of b to the x? I can bring that x down. So that's the same as e to the x ln of b. And the nice thing is that I know how to take the derivative of this using the chain rule. So the derivative of b to the x must be the same as the derivative of this thing. Right? Because writing this is just a different way of writing b to the x. Now we've got e to the something. What's the derivative of e to the something? I hope by now we're all just saying, of course, it's e to that same something. And then the chain rule says we have to take the derivative of the inside function. Do we need the product rule on x times ln of b? We don't, because ln of b is a what? ln of b is a constant. So this is like saying x times 7. Of course, normally you think about putting the constant in front. Whether you put the constant in front or at the end, it doesn't make any difference. So the derivative of x times ln of b is just ln of b. Now, is this the answer we were expecting to get for b to the x? Doesn't look quite right, but in fact, we can see that it is the same. Because now I can use that same log rule backwards, and instead of bringing the x down, I can bring the x up. So this is the same as e to the ln of b to the x times ln of b. And then e to the ln of anything, they cancel each other out because they're inverses. That is b to the x ln of b, as we conjectured. That was just based on numerical evidence last week. So I'm not going to put that in a box because it's not a new rule, but we've now actually obtained this rule in a more legal way than what we did last week by just looking at plugging values into a calculator. All right. But now that we have obtained this in a legal way, this derivative, the derivative of b to the x, that means that we can use our same technique as we did over here. If we know the derivative of b to the x, we can use the chain rule to find the derivative of its inverse. So we're going to repeat the exact same very powerful technique that we used in part 1 here. So we know that if I take b and I raise it to the log base b of x, from week 2, what are we going to get every single time? We're going to get x. So this is exactly in parallel with what we did in part 1 over there. So except that over there, I wrote this as f of x, which is what I'm going to do now here too. So this is our function f of x. I'm using the name f of x for log base b of x. So now I can take the derivative of each side. And because we know the chain rule, we're going to be able to do this. So the derivative of b to the something is what? It's b to the very same something, ln of b. Chain rule says we're not through yet. We have to take the derivative of the inside. So the derivative of the inside, we just call it the name f prime of x. And the derivative of x is still 1. So what are we trying to do here? We have the function f of x is log base b of x. We don't have a derivative rule for that yet. So we're going to try to solve for f prime of x here. So I want to move all the rest of the stuff to the other side. So f prime of x is what? It's 1 over b to the f of x ln b. But what is f of x? F of x is log base b of x. And what is b to the log base b of x? That's just x. So this is just 1 over x ln b. So that's our new derivative rule. So if you want to take the derivative of any base of a log function, this is what you will get. 1 over x natural log b. And so again, you see a place where this ln comes in, showing again why this is the natural log, why it is the most important, useful log out there. If you want to take the derivative of any exponential function, 2 to the x, 3 to the x, 10 to the x, natural log sticks its head in. You can't avoid it. If you want to take the derivative of the log base 10, log base 2, log base 23, natural log comes in again. Can't be avoided. That's why it's the natural log. It comes up everywhere. Let's do 2 more. We have. So you remember also that last week we stated the power rule, but we only proved it for positive integer values of m. So now we can use the same technique as we used for part 2 there. So we know that e to the ln, we know that another way of writing x to the m is e to the ln of x to the m, right? Because the e and the ln are inverses functions, so they undo each other. But we have our log rule, which says we can bring that m out front. So e to the m ln of x. So x to the m is the same as writing e to the m ln of x, right? So we're trying to figure out, we're trying to prove fully for all values of m what the derivative of this is. We already know what it should be, right? mx to the m minus 1. So by doing the same thing as we did in part 2, if I want to take the derivative of x to the m, that's the same as taking the derivative of this. But because we know the chain rule, and because we just recently figured out the derivative ln of x, we know how to take the derivative of this. We've got e to the something. The derivative of e to the something is e to the same something. But the chain rule says now go ahead and take the derivative of m ln of x. M is a constant. It's a constant multiplying constant. So the constant multiple rule says that the m stays there. And then we're supposed to take the derivative of ln of x, which we just figured out in part 1, is 1 over x. So that's the power rule. That's the derivative of x to the m. Does that look like how it looked last time? No, it doesn't, right? So somehow we're going to have to figure out why this is the same as mx to the m minus 1. Let's do it. So we can move this m back up using our same exponent rule that allowed us to move it down. So this is e to the ln of x to the m times m times 1 over x. But what is e to the ln of x to the m? Again, the power of inverse functions, they undo each other. This is x to the m times m. And 1 over x is the same as saying x to the negative 1, right? And what does our exponent rule say we're supposed to do with x to the m times x to the negative 1? What are we supposed to do with those exponents? We're supposed to add them. So that will become x to the m minus 1. And then if I rearrange this term by writing the m out front, there it is. That's our power rule from last week, except now we've got it for all positive integers, for all real numbers. So as we thought last week. I don't know about you, but I will sleep better tonight knowing that we've really proved this. We're not in the business of just telling you what the rules are. We want to figure out where the rules came from and justify them. One last one. We still haven't done any of the inverse trig derivatives, right? They all work the same way. I hope you're guessing what the answer is. We already know the derivative of what function? Sine. So therefore, we can get the derivative of arc sine almost for free by using the same technique we used in parts 1 and part 3. And then we'll leave it to you to do arc cosine and arc tangent on your own if you want. We'll tell you what the answer should be. So f of x is arc sine of x. We know that sine of f of x should just be x, right? If you take the sine of the arc sine of x, they should undo each other and you should get x. So we can take the derivative of each side, just as we did before. So what's the derivative of sine? That's cosine. So cosine of f of x. And then the chain rule says, let me just make a note here of what we did here. Take the derivative. Chain rule says you have to take the derivative of the inside, so that's f prime. And the derivative of x is still 1. This is exactly the same technique we did for natural log of x and for log base b of x. What are we trying to solve for here? F prime of x. So f prime of x is 1 over cosine of f of x. But what is f of x? Arc sine of x. And does this look familiar? You've got an inverse trig function inside of a trig function. Remember back in week 2, we promised you that rewriting those without trig and inverse trig functions would come in handy. Here it is. We want to rewrite cosine of arc sine of x without using any trig or inverse trig functions. So let's leave a little bit of space here to figure out what that is. And how do we do that thing like we did back then? I think we said something like let theta equal arc sine of x. So that meant that if I want to get rid of the arc sine, what do I need to apply to both sides of that equation? I need to take the sine of each side, right? So sine of theta is just x. I hope you're now thinking about what the next step is going to be. We have to draw a certain shape, don't we? Got to draw one of those right triangles. So I want to make an angle theta. Let's say we draw it down here, whose sine is x. Sine on a triangle is opposite over hypotenuse. So the easiest way to put that would be x and 1 there. And we can use the Pythagorean theorem to figure out what this side is, right? That will end up being the square root of 1 minus x squared. You could call this side y, and then you'd say 1 squared equals x squared plus y squared, and solve for y. Exactly the same you did on week 2 and on the homework. So what do we want? We want the cosine of arc sine of x. So we're looking for the cosine of theta. Cosine is what over what on a triangle? Cosine is adjacent over hypotenuse. So this is 1 over square root of 1 minus x squared over 1. Cosine of arc sine of x. So then we just get that is 1 over the square root of 1 minus x squared. So now we've rewritten the derivative without using any trig or inverse trig functions. So we can add that to our list. The derivative of arc sine of x is 1 over square root 1 minus x squared. See how it's all coming back to our knowledge of inverse functions from earlier. And then you can do the very same trick, very same technique on your own if you want to do arc cosine and arc tangent. We'll just tell you here what they will end up being so you can check. -1 comes in there. That's going to come about because when you take the derivative of cosine, you're going to get a negative sign. And then when you do arc tangent, there's no square root on the bottom because the derivative of tangent has got a square in it, right? It's a secant squared. So the secant squared ends up squaring the square root and canceling each other out. And these are the derivatives of all the functions that we promised to be able to find the derivatives of when we were doing back in weeks 1 and 2. So we've come a long way, right? Back then, we just knew how to do the pre-calculus for the functions. Now here we are, 4 weeks later, we know how to take the derivative of every one of those functions. And now we'll give you a chance to practice that in the next segment.